Hello, dear students. Welcome back to our discussion on simple aircraft refrigeration system. So, in the last session, we stopped with this ramming efficiency, which is nothing but P2 dash minus P1 by P2 minus P1. Now, let us move further through the other processes involved in our simple aircraft refrigeration system. So the next stage coming after this ramming process is our compression process, or the main compressor. Here you can see in our initial diagram explanation, this 1 to 2 was our ramming process. Immediately after that, this already rammed air, it is then compressed by the main compressor, okay, which is actuated by the gas turbine. This gas turbine was actuated by the combustion chamber. Okay, so 2 to 3 is our main compressor working. So here you can see 2 dash was the end of the actual ramming process. So immediately after the 2 dash, it is going to enter the main compressor process. So here also we will assume the compression process. The easiest way to assume it as a isentropy process or reversible adiabatic process, but we know that is not possible in an actual case. So there will be many sort of irreversibilities associated with this main compressor work. So instead of 2 dash to 3, we will assume a ideal compression. Instead of an ideal compression process, we will assume a irreversible adiabatic compression process. Okay, so 2 dash to 3 will be our ideal main compressor working, and while 2 dash to 3 dash will be our actual or irreversible adiabatic compression process. Irreversible adiabatic compression process. So 2 dash to 3 will be our ideal main compressor working, which will be isentropic. 2 dash to 3 dash will be our actual main compressor working, or irreversible adiabatic. Now let us in this compression process, now let us try to understand how we can represent the work done by this main compressor working. So our compressor is working. Let us come back to our TS diagram. Our compressor is our actual compressor is working from 2 dash to 3 dash, 2 dash to 3 dash, our actual main compressor working. So the compressor work involves PV work, or it is the main compressor is increasing the pressure volume work from 2 dash to, and increasing that pressure volume work to 3 dash. So we can write the general expression for work done by the compressor like this. Work done by the compressor will be MA, or MA stands for mass flow rate of the air. Air is nothing but our working fluid in our aircraft refrigeration system. Mass times n by n minus 1. N by n minus 1 is the exponent of that thermodynamic relation. This is a general expression written over here. M into n by n minus 1 into the pressure volume work done by the compressor, or change in the pressure volume energy of the air, which is nothing but the working fluid in our aircraft refrigeration system. So the pressure volume change happening here is P3 dash V3 dash minus P2 dash V2 dash. Okay, so here we are talking about a compressor working. Here we are assuming it as a adiabatic process, but not reversible. Okay, so instead of n, we can write it as gamma by gamma minus 1, because the thermodynamic exponent for a adiabatic process will be gamma. So times then we can change this pressure volume terms in temperature terms. So this R term we can take it outside. Inside the bracket it will be T3 dash minus T2 dash. So the work done by the compressor will be MA into Cp by R times gamma by gamma minus 1 is nothing but Cp value. So MCp T3 dash minus T2 dash. So this is a very simple relation. Now let us come to the third part, or the cooler or the heat exchanger process, and that is happening from 3 to 4. So let us come back to our diagram. So after leaving the main compressor, some amount of, or a small amount of air which is coming from the main compressor will be bled, or it will be extracted from this main compressor outlet. That is actually it is the 3 dash. Okay, from 3 dash to 4, the some amount of air which is bled or extracted from the main compressor, it will be admitted through a heat exchanger. Okay, actually this heat exchanger is nothing but a cooler compartment over here, because the air which is coming out from the main compressor, that is through the point 3, or actually it is 3 dash, it will be highly compressed. Due to that high compression, its total energy will be very high. So total energy will be very high means the pressure energy as well as the temperature of that compressed air will be very high. It is this high temperature, high pressure air which is admitted through, or it will be passed through the heat exchanger or the cooler. Okay, so what is happening here in this cooler? The rammed air which is at a lower pressure and lower temperature compared to the air coming out from the compressor, compared to the air coming out from the main compressor, the rammed air at a point 2, it will be at a lower pressure and lower temperature compared to the air which is coming out from point 3. So this rammed air which is at a lower pressure and lower temperature than the air coming from the 3, it can easily take up the heat from the air which is passing through 3 to 4 through this channel inside the heat exchanger. So here atmospheric air itself is rejecting heat to itself, that is to another flow of atmospheric air, but at a lower pressure and lower temperature. So that makes sense over here. So that makes a logic or sense, that is air from point 2 which is at a lower pressure and lower temperature is taking up heat from the highly pressurized and high temperature air flowing through 3 to 4. Okay, so this is the heat exchanger or the cooler process. So that is what is represented over here. So here there is no pressure reduction happening over here. This is a constant pressure process. There is no pressure and energy absorbing devices happening inside the heat exchanger. It is a simple heat exchange process. It will be considered as a constant pressure process. Only temperature is getting reduced. So from 3 dash to 4, it is our constant pressure line. So this is our heat exchanger or the cooler process. So let us discuss that cooler process over here. So the cooler or the heat exchanger process, it is from 3 dash to 4, the heat rejected by the compressed air to the rammed air. Okay, by the compressed air to the rammed air will be again mCp delta T, because Cp term is coming because it is a constant pressure process. Ma denotes the mass flow rate of the atmospheric air, which is nothing but the working fluid in our aircraft refrigeration system. Then T3 dash minus T4. Next main process in our aircraft refrigeration system is our expander process. Okay, so again let us come back to our diagram over here. For 4 to 5 is our expander process or the turbine process, where the highly pressurized air, okay, even though the heat is rejected to the rammed air at the cooler, the air coming from the main compressor, it is not losing its pressure energy. It is still at a high pressure energy, so it can do work on this cooling turbine, which will be actuating this cooling air fan. Okay, during this work done on the turbine, the pressure energy of the working fluid, which is nothing but air, it will be reduced. So what is the work done during work done on the turbine by this compressed air? while it is moving from 4 to 5. So that is shown over here. 4 to 5 is our ideal expansion process, okay, which will be nothing but the isentropy process. Then 4 to 5 dash will be the actual expander process. So that is we can discuss over here. 4 to 5 will be the ideal expansion process or isentropy process. 4 to 5 dash will be the actual expansion process or irreversible adiabatic process. So just like we considered our main compressor working, we can write the expression for work done by the air on the expander or the turbine will be M A into gamma by gamma minus 1 into P4 V4 minus P5 dash V5 dash. So it will be turning out to the simple expression like this, MCP T4 minus T5 dash, where MA is the mass flow rate of the air. T4 and T5 dash are the initial and final temperatures. Then finally comes our refrigeration process. Immediately after this expander, what is the next stage? This 4 to 5 is our expander working. So immediately after this expansion process, the air which is already cooled at the heat exchanger and already which is depressurized or whose pressure is reduced after passing through the turbine, it is going to enter the cabin. Cabin is the point 6 where the human beings or the passengers or the electronic payloads etc which has to be refrigerated are kept. Okay, so it is moving to the cabin and producing the refrigeration. How it is going to produce the refrigeration? It will be this air coming out from the expander at 5, or actually the point, it will be 0.5 dash. It will be coming towards 6 and takes up the heat. Okay, so what is the heat absorbed by the working fluid, that is air, while moving from 5 dash to 6? There is no pressure absorbing device or anything. There is no pressure changing device. So it is a constant pressure process. So the refrigeration process happening inside our aircraft refrigeration system is MCP T6 minus T5 dash. So this will be the refrigeration effect. So now let us now we can easily calculate our refrigeration our COP of this simple aircraft refrigeration system. COP will be nothing but refrigeration effect divided by work done by the compressor, which will be nothing but MCP T6 minus T5 dash by MCP T3 dash minus T2 dash, which will be nothing but T6 minus T5 dash by T3 dash minus T2 dash. So this is a important relation. So this is the final COP of the simple aircraft refrigeration system. T6 means what is the temperature maintained inside the cabin where the passengers, electronic payloads or anything which needs to be cooled are kept. 5 dash is the temperature at the exit of the turbine. T3 dash means what is the temperature of the air which is coming out from the main compressor. T2 dash is the temperature of the air coming out after the ramming process. Okay, so you please remember this expression and try to understand this derivation. Okay, you practice it. Thank you. Let us continue later.